Hello everyone and welcome back. Okay, so rather than wait for questions in the first 5 minutes, I will just quickly review something we did last class because we tried to analyze it using conditional probability, but then we found that the problem statement was not sufficient to do that. So I figured I should at least give a rigorous proof that that what we said was correct. And we can do that without conditional probability. So remember, the setting was 3 identical sisters. One of them, whose name is Patty, is the best tennis player of the 3. She's so good that no matter when she plays either of the other 2 sisters, Patty wins. And these 3 sisters line up in a room, one after the other, and they're indistinguishable to us, but their order in which they line up is a random permutation. So the sisters' names are Patty, Terry, and Christine, which means that when they line up, there are 6 possible ways that they could line up. We don't know which of those 6 ways it is. And then we ask, so let's call those sisters S1, S2, S3. We ask S2 and S3 to play a match of tennis. We observe the winner of that match, and then we guess that Patty is the winner. Okay? So the probability, the event that our guess is correct is the same as the event that states the winner of the match between S2 and S3 is Patty. That's who we guess Patty is, the winner of this match. So that's the event that our guess is correct. And we can just write out this event explicitly. So anytime Patty is one of these 2 sisters, she will win the match, and then the match will be won by Patty. So we just look at, these are the 6 possible permutations. In 4 of those 6, Patty is among sisters 2 and sister 3. We write that down. And so now the probability that this event happens, which means the probability that our guess is correct, is just the size of the event divided by the size of S, which is 3 factorial, or 6, which is 4 over 6 and 2/3. Okay. So that's the long way to capture the intuition that our guess is correct as long as Patty is one of the 2 sisters the second sister, the third sister in the lineup, which we kind of figured should happen with probability 2 out of 3. Okay. So that's the sort of clarification about how you can resolve that even without conditional probability. And sort of the reason that we couldn't use conditional probability, or at least the approach that I tried at the end of last class didn't work, is we didn't know what happened. We didn't have a description of what happens when Christine and Terry play each other. Does Christine always beat Terry, or does Terry always beat Christine? That wasn't given in the problem statement, so there was a certain probability there that we didn't know how to evaluate. Or it was undefined by the problem. Okay. So today I want to talk about a really important notion in probability theory, and it's one which is the cause of lots and lots of mistakes. And it's this notion of independence. So the first thing we should do is define it. And I want you to remember this definition, even though the definition is not the way in which we typically use it. But this is the definition here. If I have two events, A and B, then I say that A and B are independent if the probability of A and B is just equal to the probability of A times the probability of B. That's the definition. It may not be what you're used to. If you've seen that definition, if you've seen a definition of independence before, but it's a good one because it's universal. It doesn't assume anything about A and B. This is just the definition. Now, what you may be more used to is something that's almost equivalent, which is, let's write this, just copy this definition and say, if A and B are independent and the probability of B happens to be bigger than 0, then, well, this is just the statement of what it means to be independent. We don't need the probability of B to be bigger than 0. But if the probability of B is bigger than 0, then we can divide by the probability of B on both sides. So on this side, probability of B cancels out. And the thing on this side, this is probability of A and B divided by probability of B. That's something that corresponds to a definition we saw last class, which is actually the probability of A given B. Okay. So if we ignore what's in the middle here, then if A and B are independent and the probability of B is bigger than 0, then the probability of A given B, probability of A. Probability of B and probability of B cancels out, so we're left only with probability of A. The probability of A given B is just equal to the probability of A. Okay. So that's the definition that you may be used to, because it has a natural interpretation, which is if you tell me that B occurred, so event B happened, that does not have any effect on the probability that A occurred, right? So that's what it means. The probability of A given B is exactly the same as the probability of A. Yes, good catch. Yeah, probability of A on the right-hand side. Okay, and what does that look like? Well, remember, what is this probability of A given B? Well, that's what happens when we just focus in on, we have the whole universe, but we focus in on just the part of the universe where B happens. So that gives us this universe that looks like this. And in some of that, A also happens. And it basically says that if I look at the fraction of the universe, the total universe that A occupies, that's the same as the fraction of B that A intersect B occupies. Okay. So independence doesn't mean A and B are disjoint. In fact, that never happens unless one of them has probability 0. It means that A and B overlap, and they kind of overlap in a way where the intersection has the same kind of density of, well, the size of the intersection compared to the size of B is the same as the size of A compared to the size of the whole set of outcomes. Okay. All right, so this is the property that we tend to always use about independence, but it's not the definition. The definition is actually this. And why is this? Why don't we just use this as the definition? Well, we don't use this as the definition because it doesn't work if the probability of B is equal to 0, because then we would be dividing by 0 here. In fact, if the probability of B equals 0, then the probability of A given B is not defined. All right, so that's the definition. And you can look here and say, well, we can sort of reverse the roles of A and B as long as, let's say, probability of A is not equal to 0, then we get if A and B are independent and both have probability not equal to 0, then you get the same thing that happens, which is probability of B given A will just be probability of B. It's the same thing, just write this down, but now divide by probability of A instead. Okay, so independence between two events is a symmetric relationship. That's clear from this definition, less clear from this one, or from this, not definition, but this consequence. But as long as A and B both have probability bigger than 0, then you get this. Okay. So let's write that down in a little box, just so we remember it. If probability of B is bigger than 0, then probability of A given B is just equal to probability of A when A and B are independent. Okay, and a little bit about language, because this is what it means for A and B to be independent, and I want to be clear about terminology. We're just going to say that A and B are either independent or A and B are not independent. So the way I want you to write this is, if probability of A and B is not equal to the probability of A times B times the probability of B, then A and B are not independent. But don't say that they're dependent, or that A depends on B or B depends on A. Just say that they're not independent. All right, so let's look at a couple of examples. So we roll 2 dice, 2 6-sided dice, D1 and D2. So that gives us a probability space that we've defined before, which is an ordered pair, D1, D2, where D1 and D2 we get by taking any of the integers 1, 2, 3, 4, 5, 6. We get that the size of this set, since there are 6 choices for D1 and 6 choices for D2, the size of this set is 6 times 6, which is 36. And we had already defined this thing as a uniform probability space, and we'll stick with that definition, meaning that the probability of any particular event is equal to 1 over the size of S, which is 1 over 36. Okay. So the probability of any particular outcome is exactly 1 over 36. All right. So let's look at a couple of events. Let's say here's an event A, which is D1 is equal to 6. And here's an event B, which is that D2 is equal to 4. There's two events described in plain language. And you should, since we're talking about independence now, the question is, are A and B independent? So intuitively, we think that that's the case, right? Whatever value we roll for A does not have an effect on the value that we roll for D1 does not have an effect on the value that we roll for D2. Somehow these things, it feels like they should be independent, but we never specified that. We just specified that this is the sample space we have, and so we need to check the definition to see if this is true. So to do that, we need to test if this holds. Is the probability of A intersect B equal to the probability of A times the probability of B? So let's look at what is A. This is when D1 is equal to 6. So this is a set that looks like 6-1, 6-2, 6-3, 6-4, 6-5, and 6-6. What's B? B is when D2 is equal to 4. So this looks like 1-4, 2-4, 3-4, 4-4, 5-4, and 6-4. So we need to know the right-hand side here, probability of A times probability of B. Probability of A is the size of A over the size of S, which is 6 over 36, which is 1 over 6. That's good. So the probability that the first one comes up as a 6 is just 1 over 6. Like we expected. And the same thing with probability of B. The set B here has 6 elements in it, so the size of B over the size of S is 6 over 36, which is also 1 over 6. And what is A and B? Well, that's the set that looks like this. All the elements that are both in A and in B, and there's only one element because everything in A has a 6 at the first coordinate, and everything in B has a 4 at the second coordinate. So the only thing that has both of those is 6, 4. So A intersect B is 6, 4. The probability of A intersect B is just the size of A intersect B over the size of S, which is 1 out of 36. And now we have everything we need to test the definition. We look at probability of A intersect B. We figured that out. It's 1 out of 36. Okay, and that is equal to 1 out of 6 times 1 out of 6. And these, why did I write it like this? I wrote it like that because that's just the probability of A times the probability of B. So indeed, the probability of A and B in this example is equal to the probability of A times the probability of B. So the conclusion is, therefore, A and B are independent. And that's not a surprise. That's a case where the definition agrees with our intuition. The outcome of rolling the first one should have should not affect the outcome of rolling the second one. Someone says, shouldn't it be 1, 2, 3, 4, 5, 6? Or am I missing something? We roll 2 6-sided dice, D1 and D2. So the outcomes for D1 are anything from, oh, yeah. No, you're not missing something. I missed the number there. Maybe I stayed up too late last night. Yes, should be 1, 2, 3, 4, 5, and 6. Okay. Let's keep testing these definitions. Let's try another example of 2 events. This time, let's take A to be the event D1 plus D2 is equal to 7, and B to be the event D1 is equal to 4. So now we have an event A which depends on the value of the first die and the value of the second die. So whether or not this event happens requires knowing the value of both of these dice. And we have an event B which is entirely determined by the first of these dice. So on the surface, if we look at if we try and sniff this out, we might think maybe these things are not independent, because this one depends on the value of both dice, and this one actually fixes the value of the first one, the first die. So you might, first intuition is they're not independent, but intuition can often be wrong, and we need to therefore test this against the definition. So if we write out the set A, these are the pairs that add up to 7, and those are 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. We count those. There are 1, 2, 3, 4, 5, 6 of them. So the probability of A, like in the last example, is 6 out of 36, which is just 1 out of 6. B, we write it out longhand. We've kind of seen this one before. This is 1, 4, 2, 4, 3, 4, 5, 4, 1, 2, 3, 4, 4, 5, 4, and 6, 4. And there's 6 of those because we have 6 choices for, sorry. Let me do this correctly. D1 is set to 4, so this is 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. 6 choices for D2, so this set also has size 6, so the probability of B is 6 out of 36, or 1 out of 6. And what is the set A intersect B? So this occurs when D1 and D2 add up to 7, and D1 is equal to 4, but so that's, a system of equations, but the only solution is by setting D2 equal to 3, right? And you can just check the sets that we've explicitly done here. That's all they have in common. is not the other one, 3, 4, not 4, 3. Oh no, 4, 3. 4, 3, 4, 3. So that's all that those two sets have in common. So A intersect B is 4, 3. It's one element. The probability of A intersect B, that's just 1 out of 36, because it's the size of the set divided by the size of S. And now we can check the definition here, although we've seen it already. Probability of A and B is 1 out of 36. That's actually 1 over 6 times 1 over 6, which is equal to the probability of A times the probability of B. And then the conclusion is that, therefore, A and B are independent. So, somewhat surprisingly, these two events, which on the surface don't look like they should be independent, turns out that they are. Okay? So if I roll 2 dice hidden from you and tell you that their sum is 7, and I ask you, well, what's the probability that the first thing I rolled was a 4? You have no better chances of guessing than if I told you nothing. Right? You can ignore this advice because by this thing here, the probability of B, well, what we had done earlier, the probability of B given A is just the same as the probability of B. So knowing that they add up to 7 doesn't tell you anything about the value of one of the dice. No. So is this a sufficient condition to for independence, or do you also have to check that probability of A given B is equal to probability of A? No. This is the definition of independence. Okay. This definition implies the other thing, that probability of A given B is equal to the probability of A. It implies it when probability of B is bigger than 0. If probability of B is equal to 0, then you have a problem, because then the probability of A given B is not even defined. So this is the definition. This is all you need to check to declare that two variables are independent, or to declare that two variables are not independent. So the question is 7 the only sum that makes it independent? And the answer is yes. Let's try that. If I switch this to 5, if I tell you that the 2 dice add up to 5, then this set changes. It's actually equal to, we get a 1 and a 4, we get a 2 and a 3, we get a 3 and a 2, and we get a 4 and a 1. This set only has size 1, 2, 3, 4. So that means that the probability of A in this case is 4 out of 36. If we look at A intersect B, it's not the same anymore. So what's in common between A and B now? They add up to 5, and the first one is a 4, so that's the 4, 1. probability of this is still 1 out of 36. So we get the probability of A and B is 1 out of 36. Okay, but that is not equal to, it's not equal to 4 out of 36 times 1 out of 36. Which is the probability of A times the probability of B. So then we can conclude that A and B are not independent. So if I tell you that the sum of the two dice is 7, that doesn't tell you anything about what happened to any particular die. But if I tell you that the sum is some other number, well, 5 in this case, then that does have some effect, right? In fact, we could have, I mean, we can kind of intuitively guess that that has some effect, because if I tell you that the sum is 5, that definitely means that D1 is not equal to 5 or 6, because otherwise the sum would have to be bigger than 5. And so we kind of guess that that should have an effect, and indeed it does. So these two events are not independent. And in fact, the only value that I can put here in which A and B are independent is the number 7. And to kind of understand that, remember the big table that we drew out in one of the first times we talked about probability, the 6 by 6 table, and we saw that the numbers that shows the sums, well, the number 7 appears 6 times. It appears along that diagonal in that table, and that's what makes it work. All the other numbers appear less than 6 times. So someone says should be 1 out of 6, not 1 out of 36. Probability of A and B is still 1 out of 36. Oh, this thing. Here's where you said I should have put a 1 out of 6. Yes. This is the probability of A. This is the probability of B, but still not equal. Okay. Good. So here's a claim, I'll say, which is if A and B are independent, then A and not B, the complement of B, are independent. And we intuitively this makes sense. A and B being independent means if I tell you B happened, then it doesn't really give you any information about whether A happened. So then if I tell you that B didn't happen, shouldn't really give you any information about whether A happened. So intuitively that makes sense. If you want to prove it, you need to show that the probability of A and not B is equal to the probability of A times the probability of not B. And the probability of not B, we have the complement rule that tells us what that is. that's the probability that A so for the proof, you need to show that this is true. This is the thing that you need to prove, the thing that I put the question mark over. This part is just the complement rule. So you need to show that the left-hand side is equal to the right-hand side here. And to do that, you just fool around. So what's the probability of A? You just write that out as, in the long way, you can take the probability of A intersect B plus the probability of A intersect not B. Right? So if I want to know what's the probability of A, I can split that up into what's the probability that I'm in the intersection, that's one part, and what's the probability that I'm just in A but not in B, that's the other part. So formally I'm using the sum rule here. I write the probability of A as the union of two sets, this part and this part. That's what you do here. And well, probability of A intersect B, if A and B are independent, that's just equal to the probability of A times the probability of B. And now let us divide, or let's rewrite this. So let's isolate this part, probability of A intersect not B, because that's what we're trying to study. So that's the same thing as saying that the probability of A intersect not B is equal to, well, on this side we have probability of A, and we need to bring this thing over to the other side, so we need to subtract it. So we get that. And so on the right-hand side here, we have probability of A minus probability of A times probability of B. We have a common factor, which is probability of A. Probability of B. We have a common factor, which is probability of A. So we get there. So the probability of A and not B is equal to the probability of A times 1 minus the probability of B, which is exactly what we needed to show. It's equal to the probability of A times the probability of not B. Okay. So if A and B are independent, then A and not B are also independent. And this is, again, by using this definition of independence, we don't have to qualify that statement with all kinds of things like, well, if as long as B is bigger than 0, and well, B also should not be equal to 1, so we don't have to add all these qualifications. Use this definition of independence, although it doesn't look like maybe what you're used to. It's a clean one because it doesn't assume anything about the probability of A or the probability of B. If you use the conditional probability version of the definition, then you have to assume that one of A or B is bigger than 0. And then when you make statements like this, you have to assume now that B is bigger than 0 and it's less than 1. But we don't need that. Okay? So let's leave the claim and get rid of the proof. look at a couple more examples. Actually, no. Definitions. A sequence of events. A1 up to AN are, I'm going to say, pairwise independent. If probability for every I, j in 1 through n, with I not equal to j, the probability of AI and AJ is equal to the probability of AI times the probability of AJ. So if I have a whole bunch of events, so we've defined what it means for two events, A and B, to be independent. That's this definition up here. What if I have a whole bunch of events? What does it mean for that whole collection of events to be independent? These events are A1 through AN. Well, there it turns out that there's different definitions of what that could mean. One of them is this, which is called pairwise independence. And it just says that I should be able to take any two of those events, AI and AJ, and they should be independent. Right? This says that this is the same thing as saying the events AI and AJ are independent. So it should, pairwise independence means if I take any pair of these things, they should be independent. So that's good, but it maybe doesn't capture everything we want. Like, what does it say about if I take three of these events? What can you tell me? Like, what can you tell me about the relationship between all three of them somehow? So there's a stronger definition. Which is that I say A1 through AN are mutually independent if for every sequence of integers I1, which is smaller than I2, which is smaller than I3, which is smaller than IK, which is smaller than or equal to n, the probability of AI1 and AI2 and so on all the way up to AIK. So it says I should be able to take any subset of these events, any subset of at least two of them, that should be equal to, so the probability that they all happen should be equal to the product of their probabilities. AI1 times the probability of AI2 times probability of AIK. So that's this definition of mutual independence. And it's quite a bit stronger because this numbers I1, I2 up to IK, they just tell us what is the subset of events that I need to check, and then for that subset, the probability that they all happen has to be equal to the product of their probabilities. So if I have a big set N, and I ask you, big set of events, A1 through AN, and I ask you, are they mutually independent? If you have to check this definition, it's going to take a while, because it says you have to take every non-empty subset of those events and check that this happens. Okay. So for the singleton elements, it happens for free. Right, the subsets of size 1, that's easy, because on the left-hand side you just have probability of I1. On the right-hand side you also have probability of I1, but you also have to check all the pairs of events, you have to check all the triples of events, all the 4 tuples of events, and so on, all the way up to the complete n-tuple of events. So this here is hard to check. So for large N, this basically means you have to check every subset except for the empty set. Here, this is a bit easier to check. If you give me n events, then I just need to consider every pair. So that means there's n choose 2, which is about n squared over 2 things you need to check. Still a lot if n is really big, but doable for small values of n. Like, for instance, if n equals 3. All right? So let's look at another couple of examples. And let's say B1, B2 is a random bit string of length 2. So that means we're looking at this whole universe. It's only of size 4. It has 0, 0, 0, 1, 1, 0, and 1, 1. Okay. First thing is the value of B1. Second thing is the value of B2. Let's look at a few events. A is equal to the event B1 equals 1, which is just 1, 0, and 1, 1. B is equal to the event B2 equals 1, which is 0, 1, and 1, 1. Let's throw in a third one. C is equal to the event B1 plus B2 mod 2 equals 1. That's a long-handed way of saying B1 and B2 are different. And that event looks like this. 0, 1, and 1, 0. And I should just quickly mention, when we say random bit string of length 2, that tells us this is the universe of possible outcomes, and each one is equally likely. So it happens with probability 1 over 4 for each omega in S. All right, so we can compute all these probabilities. Probability of A is 2 over 4, or a half. Probability of B is also 2 over 4, is equal to a half. Probability of C is also equal to 2 over 4, is a half. All right, and you can ask, let's look at the probability of A and B. We're trying to figure out what's dependent and what's independent here. Probability of A and B, well, we need to figure out what's both in A and in B. So that's when both bits are equal to 1. So that means that's the probability of a 1, 1, which is 1 over 4, which is the probability of A times the probability of B, a half times a half. Therefore, A and B are independent. We can do the same thing. Let's try B and C. Well, that means if you're in B, your second bit is a 1, and if you're in C, your two bits are different. So that there's only one thing in there. That's a 0, 1, which is 1 out of 4, which is equal to the probability of B times the probability of C. So A and C are independent. And now finally, we can check probability of A and C. So A means the first bit is a 1, C means the two bits are different. So there's only one such binary string. That's 1, 0. So it's also equal to a quarter, which is also equal to probability of A times the probability of C. Therefore, sorry, this is B and C are independent, this is A and C are independent. So A and B are independent, B and C are independent, and A and C are independent. So if these are my three events, sequence of events, A, B, C, then every pair of those are independent, which means that they satisfy this definition of pairwise independence. Because each of these three things is true, so each of the three pairs are independent, we conclude that A, B, and C are pairwise independent. Now, are they mutually independent? So, do they satisfy this definition? Well, I have three of them. I have checked that every pair is independent. The singletons are somehow boringly independent. They satisfy this definition immediately. But what I haven't checked yet is if this formula holds when I take the entire set. So I need to check the probability of A and B and C. Okay, so what is that set? A and B and C. Well, to be in A, your first bit has to be 1. To be in B, your second bit has to be 1. To be in C, your two bits have to be different. So from that, you can see, well, there's nothing that's both in A and B and C, right? To be in the first two, there's only 1, 1, and, well, those two bits are not different, so those are not in C. Okay? So that's equal to the probability of the empty set. The probability of the empty set, remember the definition of the probability of an event is you just sum over all the elements in the event of the probability of that element, but you get an empty sum, and so this is 0. And that is not equal to 1 over 8, which is what we would get if we multiplied the probability of A times the probability of B times the probability of C. And so then we conclude that A, B, and C are not mutually independent. In words, each of them happens with a positive probability, but they never all happen at the same time. So the probability that all of them happen is 0, even though the probability that each one of them happens individually is bigger than 0. So this product on the right should be bigger than 0, but we've figured out that actually the probability that they all happen is actually equal to 0. All right. So we won't often, this mutual independence here, like I said, it's hard to check for large sets of events. So usually, when you get to use mutual independence is when it comes as part of the problem statement. Okay. So someone will say, you have, the problem statement will be something like, let x1 through xn be a mutually independent sequence of integers or something. I mean, somewhere in the problem statement that will say mutual independence, or somewhere in the problem statement it will say uniformly random over something, that you'll get mutual independence without having to verify for 2 to the n minus 1 subsets whether this definition holds. Pairwise independence, sometimes you'll have to explicitly check this, this definition. What does mutually independent tell us? Well, it tells us that no matter what subset of the events I am informed about, it doesn't give me any information about what happened, whether or not the other events in this, this subset, the events that I was not informed about, happened. Okay. So that's what mutual independence tells us. It's very powerful when you have it. It's very hard to show it for anything that's at all complicated, but usually it's, you get it because you define things to be that way. So when we make randomized algorithms, for instance, which we'll see, we'll assume that we have, and in fact we can, we'll assume we have a source of, let's say, a random number generator that gives us mutually independent integers between in some range, for example. So it's powerful when you have it because because it's this. You can take any subset of events. If you want to know their probability that all the things in that subset occur, it's just equal to the product of their probabilities. All right. So now it's story time. Annie, Boris, and Charlie write a one question let's say multiple choice exam. So I decide one year that my final exam is going to be a one-question multiple choice exam. So your mark on the exam is either 0 or 1. It's 0 if you guess any of the incorrect options, and it's 1 if you guess the correct option. And Annie, Boris, and Charlie are my students that year, and they're going to write the exam. So Annie and Boris are clever, and so we're going to say A is the event. Annie gets the right answer. Which is the same thing as that Annie gets 100% on the exam, or it's also the same thing as Annie passes the exam, and so on. But now we have A, B, and C. Those are the events. And Charlie, and I'll tell you that Annie's clever, and so is Boris. Each of them, if they write this exam, then 90% of the time they get the correct answer. Okay. And Charlie, unfortunately, is not as clever. Charlie only gets the correct answer 60% of the time, so with probability 6 out of 10. So maybe this is a 5 or a 10 question multiple choice exam. Well, yeah. In any case, these are the probabilities. So if I take any one of them and ask them to write the exam, this is the chance that Boris or Charlie get it right, Annie or Boris get it right, and this is the probability that Charlie gets it right. So as a professor, I am interested in the success rate of my class, and I consider it to be problematic, or somebody considers it to be problematic, if more than half the class fails. And in this case, or it's good for me if more than half the class passes. So I'm interested in the probability that at least 2 students pass, get the right answer. Okay. So I would like at least half the class to pass this exam. That means that at least 2 students have to get the correct answer. If two of them get it, great. If all 3 of them get it, even better, but really all I care about is that particular event. At least 2 of them get it. So what does that look like? At least 2 students get the correct answer. Well, that could be that Annie and Boris get the correct answer, or maybe Boris and Charlie get the correct answer, or maybe Annie and Charlie get the correct answer. So that's the probability that I'm interested in. If I want to look at what that looks like in a picture, we have Annie, Boris, and Charlie. I'm interested in that space, that part of the picture there, that's contained in at least two of them. All right. so we can do principle of inclusion-exclusion, but actually let's just work from first principles here. So what happens if I take the probability of Annie and Boris plus the probability of Boris and Charlie plus the probability of Annie and Charlie? Well, so Annie and Boris is this thing. And Boris and Charlie is this thing. And Charlie and Annie is this thing. So if I just add up these three probabilities, I'm certainly overcounting. And what is it that I'm overcounting? I'm overcounting this stuff in the middle, the A intersect B intersect C. And how much am I overcounting it by? Well, I counted it once for Annie and Boris, I counted it again for Boris and Charlie, and I counted it a third time for Annie and Charlie. So I've counted it 3 times, and I only want to count it once. So I should subtract 2 times the probability of Annie and Boris and Charlie. All right. So we've worked this out. Now, I didn't say it, but I'll assume that these events, A, B, and C, are independent. So Annie, Boris, or Charlie didn't study together. They don't have any contact with each other when they write the exam. And so that they're independent, so that these probabilities will be easy to compute, because by the definition of independence, well, these ones are easy to compute using this definition, and I'll even say that A, B, and C are mutually independent, meaning that even this is easy to compute. Just take the product of the 3 probabilities. So by definition of independence, we get this one here is probability of A times probability of B. This is probability of B times probability of C. This one is probability of A times probability of C minus 2 times probability of A times probability of B times probability of C. And that is equal to A and B is 9 out of 10 times 9 out of 10. B and C, this is Boris, who gets it correct with 9 out of 10 times, and Charlie with probability only 6 out of 10. Annie gets it correct with probability 9 out of 10, and Charlie gets it only correct with probability 6 out of 10. And then we have to take a minus 2 times 9 out of 10 times a 9 out of 10 times a 6 out of 10. And now this is a problem that you can solve with a calculator, which gives you 459 out of 500, which looks like 0.918. That's a easier way to see that fraction. So do this with a calculator, you get 459 out of 500, or if it's a calculator that doesn't like fractions, it'll give you this number here. So the probability that at least 2 students get the right answer is 0.918. So 91.8% of the time that I do this exam, and when I create an exam like this, at least half the students will pass, if these are my 3 students. Okay? Good. let's consider a different scenario. Let's consider a scenario where Charlie, Boris, and Annie are in the same room, and Annie and Boris know everything, including how good they are at these types of exams, and they each know that they have probability 9 out of 10 of getting the correct answer. So Annie and Boris have no incentive to cheat off of each other. Okay? So to copy off of each other, because if Annie copies off Boris, that won't increase her chances of getting the correct answer. And same thing if Boris copies off Annie. But Charlie does have an incentive, and let's say it happens to be set up that Charlie is seated in a place that he's close enough to see Annie's answer. So Charlie has the option to copy. Okay. All right, so that's good. So now Charlie's probability of getting the correct answer on the exam increases. Charlie's probability jumps from 6 out of 10, 60% chance, to 9 out of 10, a 90% chance. So that should mean that overall the class does better, right? I mean, that somehow should mean that the class has a better chance of succeeding, and that me, I have a better chance of the class doing well because I care about at least half the class succeeding. Let's check that out. So this is scenario 2. Boris copies Annie's answer. So what happens then? So there is no more, sorry, not Boris, Charlie copies Annie's answer. Charlie's the less clever of the three. So what happens there? Well, we think about this for a little bit. So the event that I'm interested in is still, what is the probability at least 2 people get the right answer? So, and by get the right answer, I don't mean that they figured out the right answer. I just mean that they submit an exam that has the correct answer written on it. So I don't care if Charlie cheated. So think about this for a few seconds and realize that, wait a minute, that event, this event here, only depends on what Annie does. If Annie gets the right answer, then so does Charlie, and 2 people get the right answer. If Annie gets the wrong answer, then so does Charlie, and less than 2 people get the right answer. So this here, whether the class was successful or not, it's all riding on Annie's performance now. Because she's basically counting for 2 people. So that says that under this scenario too, this is just the probability of Annie, which is 9 out of 10, which is 0.9. Okay, that's sort of an easy exercise. Why is this surprising? Well, it's surprising because under scenario 2, people should be doing better. Charlie's chances of getting the right answer jumped from 60% to 90%. And yet, the probability of at least half the class succeeding, or even in this case, even 2/3 of the class succeeding, dropped. If they all just did it themselves, then there would be a chance of 91.8% that at least 2/3 of the class would pass. But as soon as Charlie starts copying, that drops to 90%. So this is a nice example of something really unintuitive that happens. And it's happening because of the lack of independence in this second scenario. This first scenario, when we had everything mutually independent, probabilities were easy to compute. We got the answer easily. Here we have a lack of independence, and so something really non-intuitive happens. Even though individually everybody's chance of being correct goes up, somehow overall the chance of the entire class doing well, and well means that at least half of them pass, goes down. So I think that's a nice place to end it for today. So all of that to say that scenario 2, although it looks good for Charlie, it's somehow bad overall. It's bad socially. It's a bad thing for him to do, to cheat, because he somehow just increased the failure rate of the whole class in some sense. Much better for Charlie would be to just study harder and change this probability, C. If he would study hard and raise his probability to 9 out of 10, then this number would go up rather than down. All right, that is the end of the lecture today. I can answer a question or two if you like. So someone says, what about all 3 getting the right answer? Yep, this calculates that, right? I want to count the probability that 2 get the right answer, that's any of these pairs, or 3 get the right answer, that's this one, and we carefully made sure we calculated exactly that. Remember that the sum of these 3 things triple counted that event that all 3 get the right answer, so we have to subtract 2 of the occurrences. What it means if something is mutually independent. So let me try and write it another way. A1 through AN are mutually independent if for every non-empty subset, let's say X, a subset of A1 through AN. Now, there's a bit of an issue here that A1 through AN is a sequence, and I'm treating it like a set, but let's ignore that for a second. That the probability of the intersection of X in X of, I don't know, let's say A in X, the probability that all the events in that subset happen is equal to the product over A in X of the probability that those things happen. Okay. So this notation, may or may not have seen it before, it's exactly like the sum notation, the sigma notation, except that instead of adding all of its things, you multiply them all. And this is, if I give you a bunch of sets, this is just intersecting all of them. Okay. So I have a bunch of events, take any subset of them, and what's the probability that all those events in that subset occur? It's exactly the same as the product of the individual probabilities that they occur. Can I prove scenario 2 by calculation, please? Sure. So, what is this set? At least 2 people get the right answer. Well, this is, Annie has to get the right answer. So that means it can be, it's just Annie. At least 2 people get the right answer is just the same thing as Annie gets the right answer. I don't know what more to do other than to say, well, that's the same thing as saying Annie gets the right answer and Charlie gets the right answer, or Annie gets the right answer and Charlie gets the wrong answer, right? Basically, Annie gets the right answer and I don't care what happens to Charlie. And so the probability, the probabilities are the same. So I don't know what more to say. We're told the probability of A, it's 9 out of 10. Okay, so yes, someone asked me a question about this. So last lecture we talked about meeting Anil and his these events. Anil has 2 boys, and at least one of Anil's children is a boy. And I said, so basically we said, what's the probability that Anil has 2 boys, given that at least one of Anil's children is a boy? And I said, well, suppose I run into Anil in the park and I see him walking with a boy. Now I know at least one of his children is a boy. That increases the probability that his other that changes the probability that his other child is a boy. It makes it a third. So that's a little bit vague. In particular, it discounts. So it's true that when I see Anil in the park with a child who's a boy, I know that Anil has at least one child that's a boy. But there's nothing in the statement that says anything about what's the probability that Anil takes a walk with his male child, or if he has a female child, the probability that he takes a walk with his female child. If I wanted to make this really specific, if I wanted to really model this exactly the same way that the question is posed formally, I would have to say Anil is a misogynist, and if Anil has a child that is a boy, he only walks in the park with that child who is a boy. Okay. So when I see him in the park with a boy, the only thing I learn is that he has a child who is a boy. Okay. Otherwise, there's more modeling that has to come into it, and well, there's a question of, if I saw Anil in the park what's the probability that the child he's walking with is a boy or a girl given the number of boys or girls that he has as children. So let's not focus too much on these word things, because it very quickly, as soon as you leave the domain of mathematics and just talk and try and talk about real world scenarios, you realize that everything you say is ambiguous. And so let's stick with the formal definitions. Hopefully those things are correctly modeling what we would like to model, but don't read too much into the sort of stories that I tell surrounding these things. Yeah, why is Boris not taken into account? Because Boris by himself cannot make a majority. So I think you've figured that out. Boris doesn't matter. If Annie fails, then 2 people fail. Annie and Charlie fail. If Annie passes, then 2 people pass. Annie and Charlie pass. So really, it doesn't matter what Boris does. He can't carry it if Annie gets the wrong answer. So if you would like to play around with these kinds of things, maybe you have Annie, Boris, Charlie, and Diego, and maybe Charlie and Diego are 2 bad students. And look at different scenarios where both Charlie and Diego copy off Annie, maybe where Charlie copies off Annie and Diego copies off Boris. See what the best result is in that case, and see if that whether or not that changes anything. The answer is, well, with 4 students, there's a problem of whether you count exactly 50% of the class passing as a success or not. Anyway. All right, so that's it for today. I will see you either next week or this afternoon if you're in my other class.